Hello everyone, this is Workshop 9, Solutions and Titrations. So when working in the lab, scientists are often going to make solutions. They are going to combine usually two components, maybe more, but two components together to make a homogeneous mixture. That is their solution. An example of this would be adding sodium chloride to water. When you add sodium chloride to water, the sodium chloride completely dissolves. You don't see it in the solution anymore, but you know it's still there. It didn't just disappear. And so that is a homogeneous mixture. You have made a sodium chloride solution with the sodium chloride and the water. But now that you have that solution, you need to actually be able to express just how concentrated it is. How much of my solute, in this case the sodium chloride, your solute is either your minor component or usually the substance as being dissolved in the solvent then of course being your major component or what you are adding your solute to. But in this example with the sodium chloride and the water, we need to say how much solute, how much sodium chloride have I added to the water? Did I add a small amount or did I add a large amount? And that goes for any solution. If you are working in a lab, there has to be a way to express just how much solute there is in the entire solution itself. This way you don't work with something too concentrated or too dilute. And so to be able to express that, we have a unit called molarity. Molarity being denoted with a capital M. Molarity is equal to our moles of solute over our total volume in liters of the solution. The units for molarity are very precise. It has to be moles in our numerator and liters in our denominator. And it's always solute per solution. How many moles of solute, how much solute do I currently have in my entire solution here? It's not going to be just solute or just solvent. And so let's look at some examples working with our concentrations here, working with our molarity. So looking at example 1, what is the molarity of a solution prepared by dissolving 15 grams of sodium hydroxide, so NaOH, in enough water to make 225 milliliters of solution. Notice they specify of solution. I'm going to start abbreviating solution as SOLN. So, if our units are moles of solute and volume of solution in liters, we have to do some conversions here. We're working with sodium hydroxide. We're dissolving the sodium hydroxide in water, so that makes sodium hydroxide our solute. And we need moles of solute. If we need moles and we currently have grams, we have to use sodium hydroxide's molar mass. So if we have 15 grams, the molar mass of sodium hydroxide is 39.9998, and of course it could be a little bit different depending on how you round, but we are currently in grams. We want to get to moles, and so we are going to multiply by our moles of sodium hydroxide and divide by our grams of sodium hydroxide. Convert out of grams and into moles. Oh, sorry, I don't know why I put an extra G here. There we go. And so if we have 15 grams of sodium hydroxide, that means that we have 0.3750 moles of sodium hydroxide. And now we go on to our volume. Volume specifically has to be in liters. I'm actually going to change this real quick. 15.0, so 3.75. Okay. Specifically has to be in liters, and we are currently in milliliters. You're going to see this pretty often, especially when you get to the lab. Solutions will more often be in milliliters than liters because a liter is a pretty big volume. When you actually get to see how big a liter is, it is impractical oftentimes to work in such large scales. And so we often work with milliliters instead and convert after the fact when doing our calculations, like we will right now. If we have 225 milliliters, we want liters, we need to get out of milliliters, so we divide. 1 liter, remember, is 1,000 milliliters, or 1 milliliter is 10 to the negative third liters. Either way, your number should be getting smaller. We're going from a smaller unit to a larger unit. So 225 milliliters is 0.225 liters of solution. And so now we have everything we need to solve for our concentration. Molarity is equal to 0.375 moles of sodium hydroxide over our 0.225 liters of solution. And so the molarity of this specific solution is 1.67. We know now how many moles of sodium hydroxide we have per every liter of solution. Now let's look at example 2. Moving on to example 2. Now it says that a concentrated hydrochloric acid is usually available at a concentration of 37.7% by mass. The density of the solution is 1.19 grams per milliliter. And so what is the molar concentration? Molar concentration is another way of saying molarity. You will see both get used. Now this problem is a little bit trickier because they are not giving us as obvious of information to work with. Last problem, they gave us grams and milliliters outright. Now they're giving us a percentage and density. But remember the equation for percent by mass. That is mass of, I forget the exact word, but essentially mass of part. I'll say part because I can't remember the exact word at the moment. Apologies. But mass of whatever part you were looking at over mass of total times 100, right? And so if this is our mass percent equation, we can use 37.7 to figure out how to convert these into moles and into milliliters. Because if something is 37.7% by mass, you can make, saying you're making an assumption might not be the best wording, but you can use your own values. 37.7% is another intrinsic property of this hydrochloric acid solution. Density is an intrinsic property, and percent by mass is also now an intrinsic property. And so if we know that the hydrochloric acid solution is 37.7% by mass, then as long as we use values in our mass percent equation that hold this true, we can go ahead with our calculations. We don't need to know the exact mass values that we are working with right now, because concentration is also an intrinsic property of a solution. If you know the concentration, then you can change volume and change moles however you want. It should always equal back to your molarity. And so we are going to use any mass value that makes 37.7% by mass true. Easiest way to do that is to just use your percentage out of 100. If we say that we have 37.7 grams of hydrochloric acid for every 100 grams of solution, this does equal 37.7%. As long as our percentage holds true, we can use now these mass values to find moles of our solute and volume of our solution. So working with 37.7 grams of hydrochloric acid, like before, this is our solute, and so we need to convert it into moles. We divide by grams to cancel out the units. We multiply by our 1 mole, and the molar mass of hydrochloric acid is 36.46. And so we currently have 1.034 moles of hydrochloric acid. Now using grams of solution, this is what our density is given to us for. We have a conversion factor that gets us from grams to milliliters. That gets us from a mass to a volume. And so if we have 100 grams of solution, the density of the solution is 1.19 grams per milliliter. We divide by grams to cancel out, and we multiply by milliliter. 1.19 grams per milliliter is the same thing as saying that we have 1.19 grams for every 1 milliliter in this solution. And so 100 divided by our 1.19, we have, we have 84.03 milliliters, and of course, we need this in liters. So we divide by our 1,000 milliliters, and so we have a volume of 0.08403 liters. I realized I didn't put 0 for these. In this case, it doesn't really matter if I put 0. You can have kind of as many sig figs as you want, since we are assuming our own values here, but I like having a decimal place afterwards. So now we have moles, we have liters. We can again go ahead with our calculations to find molarity. Molarity will now be our moles, 0.0134 moles of HCl divided by 0.08403 liters. And so this solution, our 37.7% hydrochloric acid by mass solution, has a concentration of 12.3 molarity. 12.3 moles of hydrochloric acid for every liter of solution. So now let's finish off with example 3. On to our last example, finding molarity. Question 3, so the solution of ethanol in water is prepared by dissolving 75 milliliters of ethanol, H5OH, with a density, I'm going to write density ETOH, density of ethanol, has a density of 0.79 grams per cubic centimeter, in enough water to make 250 milliliters of solution. What is the molarity of ethanol in this solution? So we need to find moles of solute, moles of ethanol, and we need to know the volume of our solution in liters. So this is a case where, while we are still going to have a minor component and a major component, the phase of both our solute and solvent are the same. That's why we define solute and solvent as often minor component and major component. You're not always going to have a solid dissolving in your water or whatever your solvent is. Sometimes they are in the same phase, and so you have to define them a little bit differently. But we still need to get to moles, and so we're going to do something similar to what we did in problem 2. They are giving us the density of ethanol, and we know the volume, so this is a conversion factor between volume and mass. Yes, they are giving us density in cubic centimeters, but remember, 1 cubic centimeter is equal to 1 milliliter. We have a very direct comparison between the two. And so starting with our 75 milliliters, C2H5OH. Well, yes, this is going to give us the same value. I am still going to show the dimensional analysis of converting from cubic centimeters to milliliters. But again, it's a 1-to-1, so you'll still be left with 75 cubic centimeters instead of 75 milliliters. And now we can use our density. 0.79 grams per cubic centimeter. We want cubic centimeters on the bottom. We're trying to get out of volume. And our mass are 0.79 grams on top. And then, once we have, one more step. Once we have milliliter in grams, it is the same as before. We don't want grams, we want moles to actually solve for molarity. So 1 mole of ethanol on top, so it cancels out. Oh, I'm sorry, not so it cancels out, so we can have our unit in moles, because we want grams on the bottom, so it will cancel out. The molar mass of ethanol is 46.08 grams. And so in this specific solution, if we have 75 milliliters of ethanol, that means we have 1.286 moles of ethanol. And now the last conversion, same as always, or the same as the last two we've done. If we have milliliters, we need it in liters. 250 milliliters divided by our 1,000 milliliters for every liter. And we have 0.2500 liters of solution. And so now we can go ahead and plug these into our molarity equation. Molarity is equal to 1.286, or, oh, I'm sorry, this should actually be rounded to 1.29 for our 3 sig figs here. 1.29 moles of ethanol divided by our 0.250 liters. And so our molarity, let me just check that real quick. 1.29 divided by 0.2500 is 5.16 molarity. This solution has 5.16 moles of ethanol for every liter of solution. And now notice how I keep saying, or how I'm wording molarity every time we solve for it. 5.16 molarity, that means we have 5.16 moles of ethanol for every 1 liter of solution. That is because not only can we solve for molarity, but in the next problem we're about to do, we can now use molarity as a conversion factor. Similar to how molar mass is grams per mole. If you have the molar mass of a compound, you know how many grams of that compound you have for every 1 mole of that compound, just like we used here. Multiply by moles, because we want, that's our desired unit, divide by grams to get out of our current units. Molarity works the same. If you know that molarity is moles per liter, you don't necessarily have to just find molarity then. If you know the molarity of a compound, you can just break down the units. 5.16 molarity would be 5.16 moles per liter. Those are equivalent, since those are the units of molarity. That's how you solve for it, which then means you can rewrite it as a conversion factor. 5.16 moles for every 1 liter. And so now, if you know how many moles you have per 1 liter of this solution, and you're given some other volume, remember what I said before, molarity is an intrinsic property. And so by changing the volume, let's say I now have 500 milliliters of solution, you can use the concentration we just found and the volume you are given to then find how many moles must be in that solution to make sure this holds true. If I am told that I have 0.5 moles of ethanol in a current solution, and it's this concentration, we can use the moles given and the concentration we found to find out what volume that solution must be to make sure the concentration holds true. And we'll see that right now in question 4. Okay, example 4 tells us how many grams of calcium hydroxide are needed to neutralize 25 milliliters of a 0.100 molarity calcium hydroxide solution. So now notice they already gave us molarity and they want us to now find grams. They want to know how much calcium hydroxide is needed in this neutralization process here, which we will talk about what neutralization is in a bit once we get to titrations. But like we said before, molarity is moles over volume. We can rewrite this as, I'll write it over here, 0.100 moles of calcium hydroxide for every 1 liter of solution. This will always hold true, and so whatever volume we switch to, or however many moles we switch to, we can use this as a conversion factor. And so we have 25 milliliters. Of course, since our unit here is liters, we need to convert this first. Milliliters, there we go. And so that would be 0.0250 liters of solution. And so now we can go about finding our moles of calcium hydroxide. If we currently have 0.0250 liters, we now have this conversion factor here. For every 1 liter, we want that in our denominator, so our liters cancel out. We have 0.100 moles of calcium hydroxide. And now, once we will get from liters to moles, once we get to liters to moles, we will then be able to get to You know what, let me get the moles first, and then I'll do a separate calculation for mass. So 0.0250 times 0.1, we have 0.00250 moles of calcium hydroxide. And so now, since they want grams, if this specific solution has 0.00250 moles of calcium hydroxide, we of course use molar mass to get to grams. 1 mole of calcium hydroxide in our denominator, we want to get out of our given units right now, and the molar mass of calcium hydroxide is 74.098. Which means in this current solution, we have 0.185 grams of calcium hydroxide. The concentration is always 0.100 molarity. And so as long as the concentration is always 0.100 molarity, the volume and moles will change accordingly. If I start with a stock solution of our calcium hydroxide solution here, that's 5 liters, and I take 25 milliliters out of that stock solution, those 25 milliliters are going to contain 0.185 grams of calcium hydroxide, because if I have 0.185 grams of calcium hydroxide in 25 milliliters of this solution, it will have a concentration of 0.100. If you work backwards to get this back into moles, or at least just take this here, if you divide our moles of calcium hydroxide by our volume here, you will get the same concentration back. And that is how you know if your calculation was successful, if you set it up correctly. With molarity being an intrinsic property of this specific solution, changing the volume and changing the moles should always get you back to the concentration that you started with. Now we're going to focus on the second half of this workshop, titrations. Titrations are still going to be looking at concentration, but now you are looking at 2 solutions usually. You're going to have a solution that you have known information about, or at least more known information about, and a solution you have less known information about. Because the point of a titration is to find the concentration of one solution based on the concentration and information you know about the other solution. When you combine those 2 solutions together based on the mole ratio between the two chemicals, you should be able to find the concentration of your unknown part. So let's go through some definitions first. So in a titration, you are always going to have what is called a titrant. If I can spell it correctly, sorry. A titrant and an analyte. Right? In a titration, you mix together your titrant and your analyte to find the concentration of your unknown. The titrant is your known. It is what you know the most information about. A substance of known concentration used in titration. Your titrant you will always know the concentration of, because this is what we are going to use to actually find the concentration of our unknown, our analyte. Because if you know the concentration, you can pick how much of your titrant you want to add. And now, if you have a volume and you have a known concentration, remember our equation up here, volume and molarity, all that's left to solve for is moles. And so your titrant always will have known concentration, because based on however much titrant you actually add to your analyte, that will tell you how many moles of titrant you added to your analyte. Sorry, it's going to annoy me with how crooked it was. And so if titrant is our known, still crooked, oh well. If titrant is our known, then the analyte is our unknown. A substance of unknown concentration being analyzed in titration. So we have our our known part, we have our unknown part. And the way you know if you, the way you actually get to know what your concentration is of your analyte is that when you perform a titration, you are going to reach what is called your endpoint. Remember, I said before, your titrant, you know volume, no molarity, which means you are going to know how many moles you actually used. And based on the molar ratio between your titrant and your analyte, you can convert from one to the other. We've done that before. If you have a balanced chemical reaction, you can get from moles of one substance to moles of another substance. That is exactly what a titration is using. It's the same principle. You know how many moles of titrant you have based on whatever volume you added, and once you have a balanced equation between the two of these, you now know, okay, if I added this many moles of titrant, this is how many moles of analyte I have. And the way to know if you are at the point, if you're at the end point of your titration, is that you're looking for your equivalence point. You can't just use any volume of titrant. You know, if you don't add enough titrant, hold on, let me finish writing this. If you only add a small amount of titrant, and it doesn't react with all of the analyte, you don't actually know what the concentration is. You need to have equal number of moles between titrant and analyte. There has to be that correct ratio based on the balanced equation. If I have 0.5 moles of analyte in solution, let's say, you wouldn't actually know that yet, but let's say a solution has 0.5 moles of analyte, but I only add 0.2 moles of titrant, I haven't hit my equivalence point. I haven't properly added enough titrant to know for sure that all of my analyte has reacted, or what is called neutralized, and so you can't actually make a proper comparison. And so anytime you perform a titration, the goal is to hit your equivalence point. The point in titration when number of moles of OH, hydroxide, equals number of moles of hydrogen. Because I'm fixing that. Because titrations are going to occur between an acid and a base. That's why we call it neutralization when we get to equivalence point. If you react an acid with a base, they are going to neutralize each other. Hydroxide combines with hydrogen to make water. Water is a neutral compound. And since we will be focusing on strong acids and strong bases in this class, the counter ions of whatever your strong base and strong ion are going to form aqueous salts, which are also neutral in solution. So if you form water and a salt and a neutral salt in solution as your products, and that's all you have in solution, you should have a neutral solution by the end of it. You are neutralizing the acidic properties and the basic properties of your acid and base to make an entirely neutral solution. And that is the point we are trying to hit. Once you hit your equivalence point, you now know that your moles of base equal your moles of acid, which means you have added enough titrant to convert all of the analyte into its products, which means now you can actually create the mole ratio between the two. As long as these two moles are equal, you add the correct amount of titrant to your analyte to make moles of base equal to moles of acid. You can then make that comparison of, okay, I used this many moles of base, they completely reacted with all of my acid, which means I can now convert my moles of base into moles of acid. If you don't reach equivalence point, you can't make that comparison, because again, you will have some analyte still left in solution. You will not have neutralized all of it, which means it didn't react completely. You don't actually know how far the reaction went, and so you won't be able to actually make an accurate comparison. Now, in the lab, you have to figure out how you actually get here. It's not always very easy. Well, I shouldn't say that it's not easy, but there is some work that has to be done to actually figure out, have I hit this point? Because most acid-base reactions are going to be working with clear solutions. That's usually the hardest part. Outside of calculation's sake, when you are working in a lab, you need some visible indicator to let you know that you've hit your equivalence point. If you are mixing, let's say, sodium hydroxide and hydrochloric acid, both of those solutions that you're going to make will be clear. And if you mix those two together, you have no way of actually knowing when you've hit the equivalence point. You're just going to keep adding a clear liquid to a clear liquid. It's not going to do anything to indicate to you that you've hit equivalence. And so that is where our indicator comes into play. Indicator. So an indicator is a dye whose color depends on the pH of the solution. pH, remember, is a scale, or maybe not remember, we don't cover it in the class, but if you are unaware, the pH scale runs generally from 0 to 14 or 1 to 14. Lower numbers are going to be more acidic, and so if you have an acidity or pH value of 2, 4, 3, something like that, you're going to have an acidic solution. While the higher up you go, the more basic it becomes. At 9, 10, 13, like those are basic solutions. And so indicators are used to actually determine when equivalence point is hit. A good indicator will change in color between when it's in acidic conditions and when it's in basic conditions. The most common one we use, and the ones you'll use in lab in Chemistry 104, is, I believe we use phenolphthalein. Either we use phenolphthalein or methyl red, but it should be phenolphthalein. Phenolphthalein is clear at more acidic pHs, but as the solution becomes more and more basic, it shifts to a hot pink color. The equivalence point then can be determined based on when that color change happens. If acidic is clear and basic is hot pink, you want the color in the middle. Equivalence would be when it turns a light pink color. If it's light pink, that means there are equal numbers of moles in base because the acid is making it a more clear color, the base is making it a more hot pink color. And so the middle ground, that light pink, is now your equivalence point. There are a bunch of different indicators you can use depending on the titration you're performing. If you have a titration where the equivalence pH is more basic, you want an indicator that is going to have that color change at a more basic pH range. If you have a titration where the equivalence point is more acidic, you want an indicator that's going to have a color change in a more acidic range. Your indicator, the most important part, is that it has to change color as it's shifting from one pH to another. A dye that is going to change color as you cross your equivalence point. Some way of indicating that the equivalence point has been hit, as well as also being able to tell you you haven't reached it yet or you have over-titrated and gone too far. And so now our last definition is our endpoint, which is very similar to our equivalence point. Endpoint. This is just relating our equivalence point to the actual dye itself. Point in titration when an indicator shows the reaction is complete. So, endpoint is equivalence point, just looking at the actual indicator itself. When you hit your endpoint, your indicator shows the reaction is complete, which means moles of hydroxide is equal to moles of hydrogen. Basically the same definition, but one is focusing on the actual indicator's role, while the equivalence point then is focusing on what the moles are actually doing. And so, now that we have our definitions, and we understand that for titrations we're trying to hit this equivalence point to hit moles of base equaling moles of acid, let's look at some calculations. Looking at question 5, we have the following precipitation reaction. I can't remember if I just said in the last part with the definitions if titrations are always with acids and bases or often with acids and bases. They are often with acids and bases would be the correct way of wording it. You can perform a titration with any type of reaction though. That's what we're going to do with our precipitation reaction here. So we have sodium phosphate reacting with copper chloride to become copper phosphate and sodium chloride. What volume of 0.175 molarity sodium phosphate solution is necessary to completely react with 82.9 milliliters of 0.121 molarity copper chloride, and how many grams of copper phosphate will form? So there's two different things they're looking for here in this problem. The main thing to pick apart to know how to start this is, what is my titrant? What is my analyte? What do I have more known information about? What do I have more unknown information about? You're always going to start your calculations with your titrant, or what you have more information known about. You need some way to get 2 moles. Every time you have a titration, the goal should be, how do I get 2 moles from here? I can't convert from one thing to the other in this chemical equation until I know the number of moles I have, and so which information in this problem will actually get me 2 moles of one of the substances. For our sodium phosphate, they're only telling us concentration, but for our copper chloride, they're telling us concentration and volume. 0.121 molarity copper chloride. And they're telling us we are trying to neutralize, or not neutralize, completely react with 82.9 milliliters. Whatever compound has both the molarity and volume is going to be your known. It is going to be your titrant. It is what you can start your problem with to get to moles. Of course, we do have to just quickly convert out of milliliters. So we have 0.0829 liters to work with. But now we can go ahead with our calculations. We can find our moles to then go to our balanced equation here, use some stoichiometry, and get to our desired information. And so if we have a concentration of, right over here, 0.121, we multiply our concentration by our volume to find moles. Because remember, the units of molarity is that we are saying we have 0.121 moles of copper chloride for every 1 liter of solution. We are trying to get out of liters here. So really, if we want to follow this dimensional analysis way, let's start with our 0.0829 liters and use our molarity as a conversion factor. 0.121 moles of copper chloride. So this way we start with volume instead of molarity. You would get the same thing. If you multiply the molarity and then the volume, or if you do volume and set it up this way, of course, multiplication, you will get the same answer. But if writing it this way just makes it a little clearer to see why multiplying molarity by volume gives you moles. So if we multiply 0.0829 by 0.121, we have 0.0100 moles of copper chloride. Now that we have moles, we can get to our desired information. We want to know what volume of sodium phosphate is necessary for this reaction, so we need to get to sodium phosphate. We need to know how many moles we actually have to use the information given to us about our sodium phosphate. So if we have 0.01 moles of copper chloride, based on our balanced equation here, it's a 2-to-3 ratio between our sodium phosphate and our copper chloride. 2 moles of sodium phosphate for every 3 moles of copper chloride. Oops, wrong. There we go. So 0.01 times 2 divided by 3. There we go. We have I'm looking at the wrong line, sorry. 0.00667 moles of sodium phosphate. Now that we know how many moles of sodium phosphate we have, we go to the information given to us about our sodium phosphate. I think I also said before, oftentimes in a titration, you'll be looking for your unknown concentration. Of course, you can work the other way around as well. Once you have moles, as long as you have one of the other 2 values, you can find that missing 3rd value. Oftentimes it will be, you have to find moles from the different substance and they give you volume already. But in this case, we found the moles of sodium phosphate and they gave us molarity already. We can do the same thing. We have 0.00667 moles of sodium phosphate. And they tell us that sodium phosphate's concentration is 0.175, which means we have 0.175 moles for every 1 liter. Setting up our conversion factor accordingly, we need liters on top. That's what we're trying to get to. And we will put our moles of sodium phosphate on the bottom. This will now cancel out. Our concentration is 0.175, so there's 175 moles for every 1 liter. Which means we have a volume of 0.0381 liters. when you are taking the actual exam, just pay attention to your answer choices. This answer is correct, but most likely it's not going to be what they want on the exam because this is in liters and we started our question in milliliters. So really, you're more likely going to have to convert it into milliliters as a final step. But again, just pay attention to what units you are working with. And more importantly, pay attention to the units given to you on the problem. It's not likely that they're going to give you one answer choice where it's in liters and one where it's in milliliters. That would be a little bit mean, if I'm being honest. But it's always good practice to convert back into the units that you were originally given. Our copper chloride volume was in milliliters, and so this should also be in milliliters. Now looking at the second part, how many grams of copper phosphate will form? This is now just using our mole values again. Doesn't really matter which one we use. We know that based on this solution, everything is reacting completely, so we can work with the 0.0100 moles of copper chloride, or we can work with the 0.00667 moles of sodium phosphate. Both of them, we have a relationship between either reactant and the copper phosphate that we want to find the information about. I'm going to use the copper chloride moles because it's just an easier number to work with, 0.01 versus 0.00667. But this part doesn't really matter which moles you end up working with, as long as you're using a mole value, not a concentration, not a volume. So if we have 0.100 or 0.0100 moles of copper chloride, there is a 1:3 ratio between our copper phosphate and our copper chloride. We want to get 2 moles of copper chloride, so that goes in our numerator. So we're trying to get to our moles of copper phosphate. We're trying to get out of our moles of copper chloride, so that goes in our denominator. 3 moles copper chloride. These will cancel, which means we have 0.00333 moles of copper phosphate. And if this is how many moles we have, as always, if we have moles and we're trying to get to grams, we need molar mass. We're starting in moles, so our moles of copper phosphate will go in our denominator, so they cancel out. And our grams of copper phosphate will go in our numerator. And so 1 mole of copper phosphate has a molar mass of 380.586, which means if we started with our solution, if we started with our known information, knowing that for the complete reaction, we need 0.121 molarity copper chloride, 82.9 milliliters of 0.121 molarity copper chloride, for this, when this reaction goes to completion, we are going to create 1.27 grams of copper phosphate. As long as you were able to get to moles, a lot of these calculations should feel a little familiar. Moles is kind of the base unit for a lot of chemistry. If you can get to moles, you can find information about a lot of your chemical reaction, a lot about each reactant and each product, about its concentration, etc., etc. The main goal usually ends up being, how do I get to moles so I can take whatever path I need to get to the rest of the information that I need. And so that's question 5. So on to our final question, question 6. Last problem we have here, a 50 milliliter sample of an unknown phosphoric acid solution is titrated with 0.195 molarity sodium hydroxide solution. The equivalence point is reached when 48.73 milliliters of sodium hydroxide is added. What is the concentration of the unknown phosphoric acid solution? So this is a more conventional titration with an acid and a base. We are trying to reach that equivalence point, neutralization, when the moles of base are equal to the moles of acid. What point do we get to both our acid and our base completely reacting with each other and making all of their product? And so the first thing you should do with these titration problems is write your balanced chemical equation. And the first one, they gave it to us, and this one we have to write it ourselves. You always need the balanced chemical equation to know that ratio between your 2 reactants. We saw that in question 5. We had to know the mole ratio was 2 to 3 between the sodium phosphate and the copper chloride. We need to do the same thing here. What is my ratio between my phosphoric acid and my sodium hydroxide? So we have H3PO4 plus NaOH. Now, anytime you have an acid-base reaction, you are going to combine, it's going to be similar to precipitation reactions. You swap your cations. Water is always going to be one of the products, because the cation is hydrogen in phosphoric acid, and the anion is hydroxide in the base. Anion plus cation, hydrogen plus OH. You are always creating water as one of your byproducts, liquid water. Now the other product, or I shouldn't say byproduct, just as one of your products. And the other product would be the other swap, sodium and phosphate. Sodium phosphate. Sodium has a charge of +1, phosphate -3, so it's Na3PO4. Now let's create a table to see if this is balanced or not. Reactants, products. We have hydrogen. Phosphate stays phosphate, so we're going to treat it as just phosphate. Sodium and oxygen. We couldn't treat hydroxide as hydroxide because we don't have hydroxide in the product side. Remember, polyatomic ions stay as polyatomic ions so long as they maintain themselves between reactant side and product side. Hydroxide broke down, so it has to be treated as separate hydrogens and oxygens. We have 4, because 1, 2, 3, and then 4 from the hydroxide. 4, 1, 1, and 1. And now we have 2, 1, 3, and 1. Doesn't really matter where we start balancing. Hydrogen is going to be a little harder to balance since we have hydrogen split across multiple species. So I'm going to start with sodium balancing. 3 sodium on our product side, 1 on our reactant side. We are going to multiply sodium hydroxide by 3. That changes all of our values. Now we have 3 sodium on our reactant side, but we also now have 3 oxygen, and we have 1, 2, 3 hydrogen from our sodium hydroxide, and 1, 2, 3 from our phosphoric acid, so we now have 6 on our reactant side. But now it's a little more straightforward how to balance the hydrogens, because on the product side, we only have 1 species containing hydrogen. We don't have to worry about how we are going to distribute them across the 2 molecules here. 6 to 2, 3 to 1. If you multiply water by 3, now everything is balanced. And this is why we needed to write our equation. It is not a 1-to-1 ratio between our acid and base like a lot of these titration reactions will be. It is a 3-to-1 ratio now between our base and our acid. And that is going to change how we go about our calculations. Now again, we want to get to moles. If we are being told information about 2 different substances, we need to figure out how to convert between one and the other. We need to make the comparison between the 2. You can only do that with moles. We only know the volume of our phosphoric acid solution, but we know the volume and concentration of our sodium hydroxide solution, so that has to be what we start with. A 0.195 molarity solution. The equivalent point is reached when 48.73 milliliters of sodium hydroxide is added. Of course, starting with our conversion here, out of milliliters and into milliliters. So that's how many liters of our sodium hydroxide solution we added, and now we can use that to figure out how many moles were added. 0.04873, flip that backwards a little bit, sorry. 4873 liters of solution with the molarity of 0.195. That is the same thing as saying 0.195 moles per every 1 liter. We are currently in liters, so we want liters in our denominator, moles of sodium hydroxide in our numerator. For every 1 liter, we have 0.195 moles of sodium hydroxide, which means that for this 48.73 milliliter solution, we have 0.00950 moles of sodium hydroxide. Now that we know how many moles of sodium hydroxide we have, we can find how many moles of phosphoric acid we have. 0.00950 0.950 moles of NaOH. That 1:3 ratio is now going to come into play. We want to get to moles of phosphoric acid, so that's in our numerator. We want to get out of moles of sodium hydroxide, sorry. 1 to 3, 1 mole of phosphoric acid for every 3 moles of sodium hydroxide. So dividing our moles by 3, even though we use 0.00950 moles of sodium hydroxide, because it takes 3 times the amount of sodium hydroxide just to neutralize 1 mole of phosphoric acid, that means we neutralized 0.00317 moles of phosphoric acid. So now we know our moles of phosphoric acid, and they told us the volume in the beginning of the problem. And so we can go ahead and find our concentration. First, of course, they told us we were working with a 50 milliliter sample, and so we just have to quickly convert that out of milliliters.